Hi everyone, I'm Zhenni Feng from Donghua University, Shanghai, China. I feel great honor to give a presentation of our paper, An Online Truthful Auction for IoT Data Trading with Dynamic Data Owners. This is the outline of my presentation. Let me introduce the background of the data trading problem first. Data is an extremely important and valuable asset. Almost every company is aggressively turning to AI or machine learning technology to gain a competitive advantage. Therefore, data trading is a great opportunity to unlock the power of AI or machine learning and make full use of big data. Application servers, application service providers, data service providers, AI companies, government agents are possible data consumers which request valuable data from data owners. Various data sets are generated and recorded by data owners, such as web browsing history, online shopping orders, fitness records, sensory data, and trajectory data. Data trading is different from a general concept of data sharing. In a typical scenario of data sharing, an application user usually discloses his data, for example, web browsing history to application service providers passively or unconsciously to be accessible to their services. Data trading, however, makes it possible for both data consumers to specify what data they want and data owners to determine whether or not as well as how to treat their data. Existing studies have investigated how to treat private data, while authors propose pricing functions for personal data or other private data to compensate different levels of privacy losses. A few desirable properties, for example, budget feasibility, performance accuracy are considered. Recently, a lot of attention has been paid to design data trading markets or platforms based on the blockchain technology due to absence of a trustworthy and centralized data trading platforms or single point of failure. Furthermore, some existing data trading platforms have introduced the trusted execution environment, such as the hardware of Intel's SoftGuard extensions. Besides, task allocations, algorithms, and incentive mechanisms designed for mobile crowd sensing systems are also not suitable, because they focus on collecting data on demand and evaluating the value of data on cost of workers instead of the data itself. However, most of them ignore an important issue of dynamic behavior of both data owners and data requests. Here's an example. When a data request of querying real-time noise level locating at a given block is submitted, a smartphone can serve as a data owner only if the owner of the smartphone passed by the block. Consequently, we assume a data owner is intermittent and only be available to treat his data during a specific time period, which we call active time, due to limit resource or mobility. Furthermore, data requests are randomly generated by data consumers and then submitted to the data trading platform that usually runs on an edge node or a cloud server. In the paper, we model the dynamics of data owners and the data requests in the scenario of IoT data trading. Our goal is efficiently trade IoT data collected by mobile devices, while data owners dynamically join in or depart, and the data requests are randomly generated. There are several main technical challenges. First of all, the dynamics of both data owners and the data requests make the data trading process rather complicated. Then it is very difficult for the data platform to make an efficient matching between data owners and the data requests, because both the real value of data blocks and active time are private information of data owners. Finally, rational and strategic data owners are not willing to offer their valuable data or reveal their private information truthfully, except with enough compensation. Our contributions are summarized as follows. Firstly, it is the first work to the best of our knowledge, which takes account of both dynamic behaviors of data owners and randomly generated data requests in the problem formulation of data trading. Secondly, we propose a truthful online auction-based data trading approach, which not only determines the matching rules with incomplete information, but also computes proper trading prices between data owners and data consumers. We have demonstrated the proposed approach achieves several good properties, such as individual rationality, incentive compatibility, and near-optimal social efficiency through rigorous theoretical analysis and extensive simulations. Next, I give a mathematical formulation of our problem. The auction between data owners and data consumers is executed round by round. Data owners are short-sighted so that they expect to get as much profit as possible in the current round. We divide time into time slots of equal size. We also assume there is a third-party trading platform to manage the auction process. The auction in a single round is described as follows. At the beginning, the platform sends data requests to data owners. Then, each data owner generates a bid based on the information of data valuation and the active time, then sends it to the platform. The platform chooses some bids and determines the trading prices for each data block. The platform notifies data owners and data consumers of the results. Each data owner whose bid is selected uploads his data block. The data consumer pays for the data owner according to the negotiated trading price. We assume that a data requirement in reality can be decomposed into several smaller data requests, each of which can be satisfied by a single data block generated by a single data owner. Let tau j denote the number of data requests arriving at time slot j. A data owner has a valuation VI for his data block, which means that he would not treat the data block with a price lower than VI. The valuation is his private information and unknown to others. The active time of a data owner is a time period described by SI and EI, where SI and EI are the start time slot and the end time slot, respectively. The end time slot is not included. The real active time is also unknown to others. Each data owner can sell at most one data block or sell his data block at most once during the active time because of limited resources. That is to say, in a single round, a data owner submits at most one bid, while lowercase bi is called bid price. The bid price is probably not equal to the valuation Vi. Similarly, reported active time is probably not the same as a real active time. The solution must offer a matching rule and a payment rule. We use Xij, whose value is 0 or 1, to denote the matching result. A bid of the data owner I, denoted by capital BI, is selected at time slot j if Xij is equal to 1. Then the data owner should offer his data block exactly at time slot j and would be paid with a price of Pi. Specifically, the objective of our problem is to find the optimal matching with the maximum system efficiency. The objective is equivalent to minimize the sum of data valuation for all choosing bids, as proved in the paper. The feasibility constraints tell that a solution is feasible if each data owner can be choosing at most once during his active time. Besides, at each time slot, tau j data owners are choosing. Our problem cannot be solved by optimization algorithms for solving linear programming for several reasons. Firstly, valuation Vi as well as the active time information are unknown. Secondly, both data owners and requests join in the data trading process dynamically, which means Xij should be determined online without future information. Thirdly, the solution of the optimization problem above fails to provide any information about trading price. In the following, we propose a solution to determine both the matching rule and the trading price rule. The solution contains two key components. Firstly, an efficient online matching algorithm is proposed to determine the matching of data owners and data requests, supposing that each data owner truthfully reports his value and active time. Then we offer a computation scheme of trading prices and then prove that data owners would honestly report his private information, giving the trading price rule. The basic idea of the online matching algorithm is greedily selecting one with the lowest bid price from currently available data blocks to satisfy the newly submitted data request. The selection is executed at the beginning of each time slot as shown in algorithm 1. The algorithm maintains a set of active bids which have not been matched to any data request. The set is updated at the beginning of each time slot, appending or removing bits according to active time. At each time slot, the first tau j bits with lowest bit price are selected. We propose a trading price determination scheme based on critical bit, which guarantees that each data owner reports private information truthfully. The basic idea is to set a trading price of a selected bid, capital BI, as the bid price of the first bid that makes BI fails. Actually, if a bid is selected at time slot overline J according to the matching rule, saying XI overline J is 1, the critical bid of BI is a bid with the highest bid price, which are selected during the time period from overline J to EI other than BI. We analyze the proposed approach theoretically in terms of incentive compatibility, individual rationality, and the competitive ratio of social efficiency. Due to time limit, we omit the proof here. We perform several groups of simulations and report results to show performance of our approach. Let us check the sum of valuation when the arriving weight of data owners and the number of time slots is increasing. Obviously, results of sum of valuation of our approach are very close to OPT. Well, OPT is the optimal offline solution served as the baseline. To run the baseline algorithm, we must assume that we know everything, including the private information, and execute the data trading process in an offline manner. We plot the CDF of competitive ratio to show that our approach approximates the offline optimal solution in spite of running in an online manner. We can see that everyone has a competitive ratio larger than 0.5. It is obvious that a running time of our approach is much shorter than the baseline OPT. Finally, let me summarize the paper. We have proposed a truthful and efficient online data trading algorithm which not only resolves the problem of matching dynamic data owners and randomly generated data requests with near optimal social efficiency, but also determine the trading price of each data block, which ensures that the incentive compatibility and individual rationality of participants. There are several advantages. For example, considering dynamics of data owners when trading their data helps to save valuable resources of mobile devices. Trading data in an online manner is practical, efficient, and very simple, so it is easy to implement. Besides, a few limitations are listed. It would be better to remove the assumption of existence of a trusted and honest third-party data trading platform. Data consumers may prefer to get data earlier, and they thus expect to think the profit is different if they are served at different time slots. We leave these issues to future work. Thank you very much for your listening.